So we have this question here that says, prove by mathematical induction that for O n being a natural number there, 41 to the power n minus 14 to the power n is divisible by 27 there. So here, step number 1 here is that we need to show that this statement that we have is true for n equal to 1 here. So here we say we need to show that the statement is true for n equals to 1. So meaning that here, why there's n in this expression that we have here, we're going to substitute the 1. So we're going to have 41 to the power 1 minus 14 to the power 1. This will just be 41 minus 14 like this here. So this is going to give us 27 here. Now, if we look at this 27 here, are we able to divide it by 27 and it gives us a number, an answer without a remainder there? So the answer is yes here. So meaning that here, this is true for n equal to 1. Then we go to step number 2, which is the inductive hypothesis there. So step number 2 is the inductive hypothesis. So on the inductive hypothesis here, we make an assumption now that the statement is true for n equal to k here. So here we're going to say we need to show that, or we assume that, sorry, so assume that the statement is true for n equals to k. So now, since this is induction by divisibility here, we're going to write this expression that we have here, where there's n, we substitute with k. Then we equate it to 27m to show that indeed it is divisible by 27 here. So what I mean there is, I'm going to write 41 to the power k minus 14 to the power k here equal to 27 multiplied by m. So this 27 multiplied by m here is just to show that the statement that we have here is divisible by 27 here. So we can just go ahead and make 41 to the power k the subject here. So we're going to have 41 to the power k is equal to 27m plus 14 to the power k like this here. Okay. So you can leave our inductive hypothesis on this stage here. I'll show you the reason why we've done this here. So we go to step number 3. So step number 3 now, we need to show that the statement that we have here is also true for n equals to k plus 1. So here we say we need to show that the statement is also true for n equals to k plus 1. So we get the expression the way it is here, and then where there's n, we just substitute with k plus 1, and then we just start simplifying it there. So meaning that here we have 41. Let me just erase that. So here we have 41 to the power k plus 1 minus 14 to the power k plus 1 like this. So here we just start simplifying this expression that we have here. Now, we know that if the powers are adding here, okay, if we have powers that are adding, for example here, a to the power m plus n, this just simply means that we have a to the power m being multiplied by a to the power n here. So it simply just tells us that the base is the same, but the powers are the ones that are different here, meaning that here we're going to have 41 the power 1 multiplied by 41 the power k like this here. The The same thing here is going to apply on 14 here. So I'm going to say minus 14 multiplied by 14 to the power k, like this. So now, if this is the case here, we're going to have, where there's 41 here to the power k, remember in the inductive hypothesis here we have 41 to the power k is equal to 27m minus 14 to the power k there. So meaning that here, where there's 41 to the power k here, we can just substitute with the expression that we have under the inductive hypothesis there. So meaning that here we're going to have 41 open brackets 27m plus 14 to the power k minus 14 to the power k, like this here. So let me just scroll down a bit. Okay, so I'll go to the next page here. So then we have 41 open brackets 27m plus 14 to the power k minus 14 and 14 to the power k, like this. Then we multiply this 41 by everything that we have here. So we're going to have open brackets here. We have 41 multiplied by 27m plus. Now here we can't say 14. We can't say 41 multiplied by 14 to the power k, because this here has a power of a variable which we don't know what the value of that variable is. So it just becomes 41 like this and 14 to the power k here, like this, then minus 14 here and 14 to the power k, like this. So then now here, okay, so now here we have 41 multiplied by 27m plus 41 here, 14 to the power k minus 14 to the power k, like this. Now these two terms here are like terms. They both have 14 to the power k, which is treated as a variable here. So this here in a nutshell is just the same as 41a minus 14a here. So this a here just represents the 14 to the power k here. So meaning that here we have 41 multiplied by 27m, then this side here. So if we say 41 minus 14, we're going to have plus 27. So here we're going to get 27a. So in this case our a is just 14 to the power k here. So we're going to say 14 to the power k, like this here. Then here, are we able to factor out 27 here? Of course we can factor out 27 here. So meaning that we're going to have 27 outside here. Then inside here we're going to have 41m plus, then there we're left with 14 to the power k, like that there. So now once we're able to factor out to the 27 that we have here, or when you meet another question here and you're able to factor out the number that is asked in the question there, then here we just say, then this here is divisible by, this here is true for n equal to k plus 1. So therefore we say this is true for n equals to k plus 1, like this. So therefore now here say the statement is true under mathematical induction. Like this here.